Hi everyone. This video is the first in a series which is focused on exploring the concept of infinity, and in particular trying to determine if all infinities are the same or if there are different types of infinity. First, I'll be introducing some of the concepts which are at the basis of this exploration, which include sets, cardinality, and functions, but by the end of this video you'll see how these relate to comparing different sizes of infinity. So here is what a set is. A set is an unordered collection of elements. So a set is written in curly braces with the elements of the set inside of the braces separated by commas. So here's one example of a set. 1, 2, 3. And this has 3 elements, 1, 2, and 3. It's unordered, so if you were to write the elements in a different order, you would really be talking about the same set. So this set here is actually the same exact set as the first one because it has the same elements, and the fact that the order is different does not matter. This is actually not a perfect definition of a set. It can lead to some contradictions, as you can look up Russell's paradox to see what this is, but this will be a sufficient description of what a set is for now. There are a couple of features of sets which are important. It's not only numbers that can be elements. So first of all, you can have an empty set which has no elements at all. And that's known as the empty set, and it's written like this, with a 0 with a slash through it. Another thing that you can, for another thing you can say that like random things are sets. You can put like the set of rocks outside of your house could be a set. But another important thing to note is that you can have a set, let's just call it A, where the elements are themselves sets. So here's another set. So the whole thing is the set A, and think for a second, how many elements does this set have? And I can tell you the answer, which is 2. One element is the number 2, and the other is a set. And the fact that this set has 2 elements doesn't change the number of elements in A. It's just the first element is this set, the second element is 2. Then you can look further into this set and say that there are 2 elements within that, which are 1 and 2, but the set A still only has 2 elements. So the cardinality of a set is essentially what we just talked about, the number of elements inside of it. So the cardinality of the empty set is 0. That's written like this. You put vertical lines around the set, and so this represents the cardinality of the empty set, and that's 0. It has no elements. Then we can talk about another set, maybe call another set, just use the same letter, doesn't matter. 1, 2, and the cardinality of A, maybe think for a second, make sure that you understand this concept, it is 2. And now the cardinality of sets seems like a very obvious concept, but it's going to become a little less intuitive when you start talking about infinite sets. So just to give you a hint of where we're going, we want to compare different types of sets that have infinite elements. So in particular, I'll give you like a few examples of the sets we'll be talking about. One is the natural numbers. I have seen like multiple definitions of the natural numbers, which some include 0, some do not. But the natural numbers are denoted by bold font N, and it's the set of numbers 1, 2, 3, and just keep counting upwards, and there's no end. So then there's the question of like, what is the cardinality of the natural numbers? And in some sense, like, it should be infinity of some sort. And we will talk more about how exactly we deal with this later. But some of the other sets that we're interested in are this bold face Z represents the integers, which is the natural numbers plus 0 plus all the negative numbers. Then there's also the rational numbers, which is anything that can be expressed as one integer divided by another. So this could be 1/2, 3/17, and there's just a tremendous number of these, infinite, obviously. Then you can try and think, are there more rationals than integers, more rationals than naturals, more integers than naturals? And one more set worth mentioning is the reals. Boldface R is used to depict that, and that's just anything that can be expressed as a decimal. And this includes rationals, but also irrational numbers, which are infinite decimals with no repeating patterns, and yeah, they don't terminate. So this includes all the rationals, but also things like pi and e and the square root of 2. So yeah, we'll compare all of these types of sets, and in fact also their power sets. If you don't know what a power set is, that's fine. I'll talk about it in another video. But now I'll dive into why functions are relevant to this study of sets and cardinalities. Because again, when comparing infinities, you want to think about, are the cardinalities of all these sets that I just mentioned the same? And yeah, I mean, I don't want to spoil anything. It's quite an interesting exploration and proving that whether they are the same or not. But to get there, we need to study what technique we could use to prove something like this, and this is where functions come in. So a function is something that maps elements from one set to elements of another set. So you can actually write functions in terms of sets entirely. I don't think I'm going to go into too much detail about that, but these arrow diagrams, which I'm about to demonstrate, allow you to see pretty clearly how sets work. So let the elements of, let this be the set A, everything in this oval, and let each dot in this oval represent an element in A. So you can imagine that this is the numbers 1, 2, 3, 4, 5. Yeah, so that's just an example. Then the elements in set B over here will be another set. Let's say B has 4 elements. So now the function f, we can say there's a function f. Let's use a different color. And f will take elements in A and map them onto elements in B. And we can represent this by drawing arrows. What's important about a function is that it cannot do something like this. You can't have one element in A mapping to multiple elements in B. That's not allowed, because then, so if we say that this dot here is 1, then we have a notion of f of 1, the function applied to 1. And let's say this is also just 1, 2, 3, 4. In this case, is it equal to 1 or 2? It doesn't make sense. If that's like a property of functions, is that there has to be a unique output for every input. So we don't want to have 2 arrows from the same input. On the other hand, you are allowed to have arrows from different inputs to the same output. So this would be allowed in this case. If this is 1, this is 2. Let's just number all of them. And this is 1, 2, 3, 4. In this case, f of 1 equals 1. F of 2 also equals 1. That's allowed. There are a couple of terms worth mentioning. So I'll erase these arrows for now. So one term we can talk about is onto, or surjective. So a function can be onto or surjective. And what does this mean? So let's write another function f and demonstrate it with these arrows. Oh, and another property of functions that you should know is that every input has to have an associated output. So there has to be something coming out. Right now, this does not represent a function because there's f of 5 is undefined. So f is not a function on the set A, with the set A as a domain. So then you just need to add one more arrow 5. So this is an example of an onto or surjective function. What does that mean? It means that every element in B has something mapping to it. There's something that maps onto every element in B. That's why it's called onto. Surjective is a more complicated formal term, but it means the same thing. So yeah, I think I don't think I had anything else to say about this. Yeah. Then let's erase this and come up with another arrow diagram to represent our next concept. So this time let's have 4 elements in A and 5 elements in B. So this time let's have the function f. Oops, that wasn't very clear. With it's pointing to the first one. So this is f again. So this is a function now. I said that every input has to have an associated output. The same is not true for the output. This element in B has nothing mapping to it, but that's allowed for functions. So this function here is called one-to-one or injective. And what that means is that every element in A maps to a different element in B, which isn't necessary for a function, but it is necessary for a one-to-one function or an injective function. Now, it's worth noting, a term you may have heard with regard to functions before is a range. So in this case, the range would be these 4 elements here. It's the 4 elements that are mapped onto. The domain is all the elements in A. And there's a separate term called codomain. And this is different from the range. The range in this case is the entire set B. The range is these 4 elements in B. The codomain is the entire set B. And this includes elements of B which weren't mapped onto. That's just a side note, not super relevant. And now there's one more term, which is bijective. And this is just the combination of both surjective and injective, or onto and one-to-one. A function is bijective if, so we can make this bijective by just removing this element here. And you can see now, is this onto? Yes, every element in B is mapped onto. And is it injective? Is it one-to-one? Yes, because every element in A maps to a different element of B. So that's what it means for a function to be bijective. And you see, to make this function bijective, we are forced to have there be the same number of elements in B as there are in A. And so this actually tells you how to prove that 2 sets have the same cardinality. If there exists a bijective function from set A to set B, between set A and set B, then the cardinalities of A and B are the same. So if we want to show that 2 functions have the same cardinality, then we just have to demonstrate that we just have to come up with a function which is bijective between the 2 sets. And if we want to show that they don't have the same cardinality, you have to prove that there's no function that can, no bijective function that can map between the 2. Just another side note, if a function is bijective, that also means it's invertible. Essentially, you can think of that like taking all these arrows and flipping their direction, taking the arrowheads off of this side and putting them on this side. And then it would map from B to A, and it would still be bijective. So this is kind of the tool that we're going to use going forward to determine and compare the sizes of sets like the naturals, the integers, the rationals, the reals, and their power sets. We're going to try and come up with bijective functions between them to see if there is a bijective function between any 2 of these sets, that means that they have the same cardinality. It's the same type of infinity. And on the other hand, if we can prove that there's no bijective function between them, then that means that they have different cardinalities. And it may be kind of hard to, how do you prove that there's no bijective function? We will see some techniques for doing that, but yeah, that's, I believe, all I have to say for this video. Thanks for watching.